The Earth System, a video series for educational institutions for free use presented by the German Geological Society, the DGGV. Hello everyone, I welcome the viewers of another episode of my video series on the Earth System. In this video I would like to take another look at the plate movements on Earth in a larger global context. It is about the seamount and volcano change discussed in the previous chapter, which shows us not only the absolute direction of plate movement, but also other connections in the global interaction of the plates. Here we see the directions and velocities at which the plates are moving today, based on the Hotspot reference system. So we see here the absolute plate movements. For example, you can see that the Pacific plate is drifting relatively quickly in a northwesterly direction at up to 10 centimeters per year. The African plate, on the other hand, is moving quite slowly, mostly at less than 10 centimeters per year. And what is interesting, it is moving slightly westwards and not eastwards, as one might initially assume when looking at the spreading zone between Africa and South America. The South American plate is of course also moving westwards, but much faster than the African plate. And this difference in absolute plate movement means that the spreading center remains in the middle between the two continents of Africa and South America, since at both sides the same amount of oceanic crust is formed. The central graben of the spreading axis, however, is moving westwards in the global pattern. This figure illustrates the principle behind it. Both continental plates move in the same direction, but the left one moves much faster than the right one. New oceanic crust is formed in a spreading zone between the two plates drifting apart, whereby the divergence movement is symmetrical at the spreading center because the same amount of oceanic crust forms on both sides. This movement is the relative plate movement between the two plates. The situation between Africa and South America is similar. We see the spreading center remains in the middle between Africa and South America. The South American plates move westward, where the African plate remains more or less stationary. In fact, it is a little bit more complicated than shown here, but in principle, it works this way. We can understand this quite well by looking at a submarine ridge in the South Atlantic, the so-called Wolfish Ridge, which extends from Hotspot to the African coast, finally extending into the basaltic rocks of the Atlantic Plateau. The hotspot is today located entirely on the African plate, approximately in the area of the islands of Tristan da Cunha and Gough Island. Here you can see the age data that were determined from samples from the seamounts. The closer we get to the Atlantic Plateau in Namibia, the older are the rocks. In general, an age trend becomes apparent that continuously increases from the islands to the Atlantic Plateau. Here I have drawn the hotspot tracks as colored lines. Between 40 and 50 million years, something happened, namely the direction of the hotspot tracks changed a little. And from around this time onwards, the hotspot forming the Wolfish Ridge is completely under the African plate, and therefore the South American plate no longer receives any material from the hotspot, which could have supplied a volcanic chain. If we look at this situation from a little further away, we can see also other hotspot tracks in the Atlantic and also in the Indian Ocean and the Pacific. And they all have a characteristic kink in a similar orientation at about the same time, around 45 million years. There are also a number of such submarine volcanic chains in the Pacific, as can be seen on the bathymetric map here, and which we know now are hotspot tracks. And the same picture emerges here in the Pacific. Many of the volcanic chains formed over a long period of time show a characteristic kink in a similar orientation at about 40 to 50 million years. Here I marked all the hotspot tracks in the Pacific where you can identify the kinks. But what is the reason for these kinks? It is a result of a massive reorientation of the plate movements, and since all plates are somehow connected to each other in a global context, this affects almost all plates on Earth. The most likely reason for such a major change in direction is the collision of the Indian plate with Eurasia, which took place around 40 to 50 million years ago. The Indian plate drifted at a maximum plate tectonic velocity of more than 20 centimeters per year towards north and was abruptly stopped by the collision in the Eocene. This event then led to a change in the direction of movement of many plates. This is undoubtedly most clearly seen in the Hawaii Emperor volcanic chain. Here the kink can be dated quite precisely to 43 million years ago. The yellow dashed lines show the Hawaii Emperor volcanic chain in the Pacific and the Wolfish Ridge and Rio Grande Rise in the South Atlantic. Above, the development in the Cretaceous and Paleocene, and below in the Eocene. All three plates, Pacific, African and also South American plate, moved in different directions after this collision as before. The Tristan da Cunha Gulf Island hotspot was exactly on the ridge axis until the collision, which led to the formation of the twin ridges Wolfish Ridge and Rio Grande Rise. After the collision, however, the spreading zone moved westward and away from the hotspot. From this point on, the volcanic chain continued to form only on the African plate. This brings me to another aspect that highlights the different orientations of volcanic chains and transform faults. Here we see the South Atlantic again with the Wolfish Ridge and the Rio Grande Rise. The hotspot tracks are drawn here schematically with a blue line. I have also entered the plate movement directions and velocities here, so you can also clearly see the difference between relative plate movement as we can observe at the spreading ridge and the absolute plate movement, which shows us that the African plate is moving slightly westward today while the South American plate is drifting much faster westward. The difference between the two movement speeds gives the speed for the relative movement as already shown. I would like to illustrate this connection with a short animation. We see three plates here that are moving away from each other. The spreading velocity is the same at all three spreading centers, which meet at the triple junction in the middle. There is also a hotspot under the branch that goes downward in the figure, which repeatedly causes volcanoes to form directly at the spreading center. And moreover, this spreading ridge is also offset at a transform fault. In the animation, the plate movement is related to the hotspot, which always stays in the same place, as is assumed for the hotspot reference system. You can see that the volcanic chain develops parallel to the trace of the triple junction, which, as I explained in chapter 4.4 on the geometry of triple junctions, also reflects the absolute plate movement. The transform fault, which remains constant in length, however, moves away from the hotspot and forms an angle to the volcanic chain, which represents the hotspot trace. And this is exactly what we can see in the South Atlantic. The track of the Tristan da Cunha Gulf Island hotspot is not parallel to the transform faults or fracture zones at the Mid-Atlantic Ridge. Here I show again the final stage of the model just shown, which I have to turn around first and perhaps to enlarge a little bit to see it better. I think the agreement between the model and what we see here in the hotspot tracks and transform faults or their extension in the fracture zones is very clear. The model shows clearly that the absolute plate movements do not have to run parallel to the relative movements. Okay, this is enough for directions of plate movement. With the next video, I would like to start a new chapter in which I will explain the process of subduction at convergent plate boundaries in more detail. So for this time, thank you for listening, and I'll be happy if you stick around. I recommend continuing with the next major chapter, which deals with the process of subduction.